Okay, lesson D here in our unit on rates of change, limits, and derivatives. We're finally going to look at how you evaluate limits algebraically. So up until now, we have been evaluating limits using tables and using graphs. Let's try evaluating them without tables and graphs. And as we're doing this algebraically, we also want to be aware of how we know algebraically that a limit does not exist. We know it doesn't exist when we're doing the table if when we approach from the left and from the right, our trends are going to two different numbers. Same thing with a graph. If we approached it on the graph from the left and on the graph from the right, and the two branches of the curve were tending towards different numbers, we knew our limit did not exist. How do we recognize this algebraically? So there are basically three strategies that you need to know for evaluating limits algebraically. Okay? And they're in this order. Number one is what is called direct substitution. You take that value that you're making x getting closer and closer towards, you sub it into your function and see if you get an answer. Always try that first, because if you get an answer, chances are that's going to be what your limit is. If that doesn't work, or it's going to give you something that is an answer that doesn't make sense, try simplifying or canceling the function that you have. Often this is going to involve doing a little bit of factoring. Okay? Third, and one that you're rarely going to use here, you might have to rationalize the denominator or multiply by the conjugate to simplify your function a little bit. And we're going to take a look at an example of what that actually means towards the end here. So our first example here, number one. Limit as x goes to 3 of 2x squared plus 3. The first thing we want to try is direct substitution. Just take our value for x, the value that x is tending towards, sub it into our function for x, and see what we get. So once we sub that x, or that number, into our function, we are no longer taking the limit. We have evaluated that limit. So at this point, we can just say, I think that this limit is equal to 2 times 3 squared plus 3. And what kind of an answer do we get here? 3 squared is 9. 2 times 9 would be 18. So if I add those up, I get 21. 21 is a perfectly good number, so that's going to be the value for our limit. Okay? It's that easy. If only they were all that easy, right? Let's look at our next example here. Slide this up a little bit here. We've got a function here, x plus 2 divided by x squared minus 4. We've seen this function before in the last lesson. We want to evaluate two limits here. The limit as x goes to negative 2 of our function, and then we're going to evaluate the limit as x goes to positive 2 of that same function. So first thing we might try is we might try just subbing in x equals negative 2. So if we do that, let's just do f at negative 2 here. We would get negative 2 plus 2 divided by, let's see, negative 2 squared would be 4 minus 4. And that gives us 0 divided by 0. Okay. Anytime you get something where you're dividing by 0, you've got a problem. Okay? This is not going to work just by doing substitution, because you can't divide by 0. Okay? Try it on your calculator. Smoke will come out of the screen or something like that. So when you see this after doing your substitution, you know that you've got to use one of the other methods. So this is where the next method we go to is method 2, where we try factoring or simplifying. So I'm just going to rewrite this. Limit as x goes to negative 2 of our function, x plus 2 divided by, and what can we factor here? Well, we can factor the denominator. X squared minus 4 factors as a difference of squares. So it factors as x minus 2, x plus 2. Which is convenient, because now we've got an x plus 2 on the top, we've got an x plus 2 on the bottom. We can cancel those out. So our limit becomes the limit as x goes to negative 2 of 1 over x minus 2. Now, I still have to write this limit as x goes to negative 2 stuff every time, because I haven't started to evaluate the limit. I've just done some algebraic rearranging here. Okay? But when I get to this stage here, now I can do the substitution step. Okay, I can take x equals -2, sub it in there, and I get a perfectly reasonable answer out of it. So at that point, I'm evaluating my limit. I can sub in -2, and I get, what, -1/4, okay, as the value of our limit. Okay, so just a little bit of factoring and simplifying, and then you can do your substitution. Now, let's see what happens when we evaluate this second limit over here, the limit as x goes to +2 of f at x. And I'll switch colors here. So this is going to be the limit as x goes to +2. Again, we can factor and do the canceling, so I'll just write out the factoring step. X plus 2, x minus 2, x plus 2. Again, we're doing our canceling. So we have the limit as x goes to +2 of 1 over x minus 2. And now we're ready to do our substitution. So what happens when we do our substitution here? What do we get, Liam?
0 over 0.
Not 0 over 0.
1 over 0.
1 over 0, right. I'll just write this out. Okay, 1 over 0. Can we do 1 divided by 0? No, we can't. Okay, so there are ways of evaluating limits that give you answers like this. You don't need to know any of them at this point. That's something you're going to learn in university, okay? So at this point, we're just going to say that if we've tried doing the simplification and we still get something that's not going to work, this thing does not exist, okay? And we saw that from the graphs. This was the one where we had the two branches of the curves. One went off to positive infinity, one went down to negative infinity. This limit didn't exist. Same function as in the last lesson. Okay, so that's 2 of the 3 techniques. So let's sort of apply these things here. Example 3, evaluate these limits. The limit as x goes to 1 of 3x squared plus x over x. Limit as x goes to 0 of 3x squared plus x over x. The first one here, what would you try first? Substitution. Is it going to work? Well, let's try it and see. We substitute in x equals 1. We get 3, 1 squared plus 1, all divided by 1. This looks like it's going to work, right? So we can just add, what, 3 plus 1 gives us 4. 4 divided by 1 is just 4. We're good. Our limit is 4. Okay. What about our second limit here? Limit as x goes to 0 of 3x squared plus x divided by x. What are you going to try first here? Ryan? Yeah, why simplify or cancel? What happens if you just do substitution? You're going to have 0 in the denominator, and it's not going to work. So let's try some factoring here. How are you going to factor this guy, Ryan? Yeah, common factor out the x. So I get 3x plus 1 on the top, and then my x's cancel out. So I'm evaluating the limit still as x goes to 0 of 3x plus 1. Now I've got something I can do that substitution on. I'm just going to sub in that 0. Right? And remember, as I sub in that 0, that's when that limit as x goes to 0 disappears. Okay? Because at that point, I'm no longer tending towards 0. I'm sort of evaluating that limit right at 0. So I get my final answer, 1. Okay. Okay. Not too bad. So this is a lot less work than making a table, right? Now, occasionally, you will get something that looks like this. This is the limit as t goes to 0 of the square root of t plus 2 minus root 2 all divided by t. What are you going to try first? And will it work? Okay, Well, first thing I would try is, I would try substitution first. Substitution isn't going to work because we've got that t down in the denominator, and I'll end up dividing by 0. Next up is trying to factor. Factoring, I don't even know how you would factor this thing. I mean, those square roots are going to give you a lot of trouble. Okay? So anytime you see square roots, I think you're going to want to use either rationalizing or multiply by the conjugate. And this is an example where you're going to multiply by the conjugate. What is the conjugate? If I've got this term on the top, square root of t plus 2 minus root 2, the conjugate of that is the square root of t plus 2 plus root 2. Okay? The exact same terms, just with the sign changed in between them. Okay? I'm going to multiply by that top and bottom. Root t plus 2 plus root 2 down on the bottom. Okay, so I'm basically multiplying by 1 here. What's going to happen as I do that? Well, we're still taking the limit as t goes to 0. Okay. If I multiply, I'm just doing FOIL here, right? So my first two, I got root t plus 2 times root t plus 2. That's going to give me t plus 2. If I do the two outside ones, I get plus root 2 times root t plus 2. And if I do the inside ones, I get negative root 2 times root t plus 2. So those two inner terms are going to cancel each other out. And I'm just going to be left with, see, my last two terms, negative root 2 times root 2 is negative 2. So when you multiply by the conjugate, you always know that those two terms are going to cancel each other out, and you're going to be left with the first term squared minus the second term squared. On the bottom, though, we're going to have t times root t plus 2 plus root 2. Okay? What can we do from here? The numerator can be simplified a little bit. We're still doing the limit as t goes to 0 of t over t root t plus 2 plus root 2. And you might say this hasn't helped us at all. This looks just as complicated as it did before. But there is one thing that we can do now that we couldn't do before. We've got a t in the numerator. We've got a t factored out in the denominator. Those are going to cancel out. So we're still taking the limit as t goes to 0, but now we've got 1 over root t plus 2 plus root 2. Now we're to a point where we can do substitution. We can take this 0, sub it in for t, and we're going to get something that we can actually evaluate. 0 plus 2 plus root 2 is just going to be 1 over root 2 plus root 2, or 1 over 2 root 2. And that's our final answer. Okay. So you sort of mess around with the function a little bit until you get something where you can actually do the substitution and get a sensible answer. And then you do that substitution, and you're done. Okay. All right. Yes?
How did you end up with only a t at the top?
Last example. So here we've got an unusual function. This is what is called a piecewise defined function. We have defined this function with two parts to it. Piecewise. Our entire function, it has the form x squared plus x when x is less than or equal to 2, and when x is greater than 2, our function looks like 3x plus 1. We want to find the limit as x tends to 2 of this function. So we can think of our two branches as a left-hand branch, okay, because it's to the left-hand side of x equals 2, this number we're heading towards, and we've got a right-hand branch because it's on the right-hand side, or greater x values than this x value that we're tending towards. So it makes sense to split this limit into two limits. The limit as x tends to 2 from the left of our function, and the limit as x tends to 2 from the right of our function. I could actually label these left, right. Now let's say we're doing this limit as we approach 2 from the left-hand side. In here for f at x, we want to use the left-hand branch of the function. We want to use that x squared plus x. So we're doing the limit as x tends to 2 from the left of the left-hand branch of our function, x squared plus x. What is that limit going to be? First step, we try direct substitution. Is direct substitution going to work here? Marine's nodding her head. Yes, it is. We can just plug in that 2. 2 squared plus 2 is 6. Excellent. If we want to evaluate this limit as we approach from the right, what are we going to have to use here? We are going to have to use the right-hand branch of our function. So instead of using x squared plus x, we are going to use 3x plus 1. So we've got the limit as x tends to 2 from the right of 3x plus 1. Can we evaluate that limit? Marine's nodding her head again. She says, what's it going to be? Yeah. 7. Yeah. 3 times 2 plus 1 is 7. So what's our limit? Is it 6 or is it 7? Malcolm.
Does it not exist?
It does not exist. It's got to head to the same value from both the left and the right. So we can sum this up by saying the limit as x tends to 2 of our function does not exist.